magnetic fields. So magnetic fields, calculating magnetic fields can be pretty difficult, mainly because it's got that cross product in there. So, but we need to do it anyway. So I'm going to calculate the magnetic field due to a long wire. So like this, like a wire of length L, and then we'll see what happens when it gets to an infinite length. And then we'll do the fun part, we'll do it numerically. And if this goes too long, I'll do the numerically in the second video, but let's just see how it goes, and let's get started. Okay, let me turn this off. So here I have my long straight wire. It's a length L, and it's got a current I going through it. So the first thing is this is the magnetic field due to a moving charge. So this is a constant, mu naught over 4 pi, which is 10 to the negative 7th. And then it's QV, where Q is the charge that's moving and V is the vector velocity that is moving. R, the vector R, is where you want to find the magnetic field. So if I put this right here, let's say that's my, well, it's hard for this particular case. Let's say a moving charge. Here's QV going like that. QV is like that. And then maybe R is over here. And that's the location where I want to find the magnetic field. And then so it's QV cross R. That's the vector cross product. Okay. And then R, again, R cubed. So there's actually two ways to do this. You could say QV cross R hat over R squared. That's totally legitimate. Or I like this one, QV cross R divided by R cubed. That way you don't have to find R hat. It ends up being the same thing. Now, if I take a long wire, I can't find the magnetic field for it. We're going to do that as a problem. But if I take a super short piece of wire, super short, and it has a length dl as a vector, which is the direction that the wire is pointing in the direction of the current, then I can say I dl, the current, which is charge per second. That's really what it is, coulombs per second, times the length of meters, gives me the same units as Q times V. So this actually turns out to be the same thing. I delta L is the same as QV. So if I have a super short segment of wire, then the magnetic field is mu naught over 4 pi I delta L cross R over R cubed. And so we have to do delta L, right? Because this part of the wire is a different distance and with a different direction than this part of the wire. So there's no wire. Where's the wire, right? There is no one wire. It's a whole bunch of tiny wires connected together. And that's why this makes this problem really more challenging. So let's say that I'm going to call this the XY direction. So this is a distance X away from the center of that wire. And I want to find the magnetic field. So I can't do that. So instead what I'm going to do is break this into tiny little pieces and find the magnetic field due to each piece and then add them up. I'm going to take the limit as the piece size goes to 0, which makes this sum an integral. Okay, let me just start on a fresh, clean sheet of paper. So here's my wire. And this is the y-axis. And this is the x-axis. And this is my observation location right here. So that's a distance x. Now, I want to pick a piece right here. And that's delta L vector. And the current is positive current going up. So let's write down my equation. B equals mu naught over 4 pi I delta L. Oh, my light went off. That's sad. Oh, you can still see. I delta L cross R over the magnitude of R cubed. Okay, so I need delta L, I need R. So let's get delta L. Delta L is this way. So delta L is the vector 0 dy 0, right? Because that's the length of that is just going to be some differential amount dy in the y direction. So that's my vector. Now what about R? So this is the vector R. So I actually have two things. I have R of the piece, let's call that RL. And then I have this vector, R of the location, of the observation location, RO. So RL is going to be equal to the vector 0, y, 0. Okay, because that's the distance from here to that point. And I can change that y throughout that whole thing. If y is down here, y would be negative. Okay, and this is different than that, right? Those are different things. This is where the piece is. This is the length of the piece. They happen to be in the same direction. RO, the observation location, is going to be x, 0, 0. It's just on the x-axis, so that's pretty easy. So then the vector r is just going to be the final position, RO, minus the initial position, RL. So I just need to subtract these two vectors. So I have x, 0, 0, minus 0, 0, 0, y, 0, and I get x, negative y, 0. That's my r. Okay, so now I have to do let's do the next thing, I delta L cross R. So that's the cross product. Now, you can memorize the cross product formula. I would be cool with that. I always memorize it as the determinant of the following matrix, x hat, y hat, z hat, and then I put my components of my I delta L. So I'm going to bring the I out front. So then delta L is 0, dy 0, and then I have the other component x negative y, 0. Now I'm gonna expand this about each term up here, and so I get, let's do the x. I expand about that. I get dy times 0. 0 times negative y is 0, and then I expand about y, and it's actually opposite. There's a Jacobian negative 1 to the 1 plus 1. It's what? Negative 1 to the 1. Well, it's 0. It's negative. So that's going to be 0 times x minus 0 times 0, still 0. And then I get the z component. I get 0 times y minus x times dy. Minus x dy. So that is my cross product up here. And it's only in the z direction, you'll notice. Because if I take this r and that delta L, then the cross product is either going to be into the page or out, because it has to be perpendicular to both vectors. So in this case, it's actually going to be into the page in the negative z direction. So now I can write my b as this. B vector equals mu naught over 4 pi. I've already done this cross product. I'm just going to put it down here. I have the I, and then I'm going to put let's put the x dy. And then I'm going to divide that by the magnitude of r, which I haven't found, cubed. And then I have to multiply that by the vector 0, 0, negative 1 to make it a vector again. And this is important. So we only have a magnetic field in the z direction, right? So I don't have to worry about the x and the y direction because they're both 0. So I'm just going to drop the vector notation and just find the scalar magnitude. We already know the direction. Okay, and that direction doesn't change, right? Because even though I get down here to negative y values, this doesn't change because there's no y in there. X is always positive, so it's not going to change direction. So I can. This is always going to be constant. Okay, now let's find the magnitude of r. Well, I already have the vector r, so the magnitude of r is just going to be this squared plus that squared, square rooted. So it's the square root of x squared plus y squared. Okay, let's put this all together, and I get the magnitude of b is mu naught over 4 pi that's not an I x dy over this cubed, which is going to be x squared plus y squared to the 3 halves. And that's actually dB. These are all dBs, right? Because that's just the magnetic field just due to that one little piece. This is dB. Yep. Okay, so now I can find the magnitude of the magnetic field by integrating both sides. So this will just become the magnitude of the magnetic field, and I want to integrate from y equals negative L over 2 to y equals L over 2. Let me write that integral on another piece of paper, which I ran out of paper. I'm so sorry. That was my mistake. Okay. Let's rewrite the whole thing. So I get b equals the integral b equals, I'm going to pull all the constants out front. So I have mu naught I should point out right here, what is the integration? I'm integrating over y, not x, right? X does not change. X is this value. It's always the same. It's constant. It's a parameter. So in the integral, I can actually pull it out. So I pull that out front, x, and that's over 4 pi. Now I can integrate from y equals negative L over 2 to L over 2, and I have dy over x squared plus y squared to the 3/2. Okay, so that's not a trivial. You can't do u substitution, right? Because the derivative of this is not up there. So I'm just going to use an integral table. I pre-looked up this one because I didn't want to look for it. This is my my CRC math table book. You can do this online too, but I'd like to show you that these things do exist. So right here, it has a list of integrals, and you see like the form containing square root of a plus bx. That's not it. Then you have a plus bx or c plus dx. That's not it. I circled that one. I don't know why. This is actually my old book. What about this one? dx over x plus or minus a squared cubed. That's what we have, right? Except that here I don't have a squared, I have x squared. Here I don't have x squared, I have y squared. So this is the same thing. So let's just write down the answer. I'm going to put it over here so I can see it. So I'm going to get b equals mu naught I x over 4 pi. And then the integral is going to be equal to, they say x, which is y, over a squared, which is x squared, square root of x squared, which is y squared, plus x squared. I'm pretty sure that's right. There's a chance I made a mistake. And if I did, you can fix it as a homework. See, that's what's great. I can just say, oh, do it for homework. And this goes from negative L over 2 to L over 2. This is y is negative L over 2 to L over 2. So let's just write this out. B equals mu naught I x over 4 pi. Now I'm going to put in my my value for L over 2, and I get L over 2 over x squared times the square root of L squared over 4 plus x squared. Right, because that's, yeah. Minus negative L over 2, so I get plus L over 2, all of that over x squared, square root, again, L squared over 4 plus x squared. And so these are the same thing, so I just get 2 of them. And that's fine, because that cancels right there. I think. Huh. Oh, and then here's... I feel like there's an error here. Mu naught I x over 4. And then I get, let's just write this as 2 L over 2. X squared. Should I factor out that? Nah, let's not. X squared times the square root of L squared over 4 plus x squared. Those twos cancel. I think that's something wrong here. Okay, well, let's just proceed. Even if it's an error, we can learn things from errors. Okay, so now what about the case where L is much, much greater than x? So an infinitely long wire. So if L is much, much greater than x, then this whole thing right here is going to be just L squared over 4, because it's going to be L over 2, right? Because I'm going to get L squared over L over 2 quantity squared. That term doesn't matter. I take the square root and I get L over 2, and then the L's cancel. Yeah, and then the L's cancel. So I get equals mu naught I x over 4 pi. Then that canceled. The 2's canceled. And then I get I messed up. Hold on one second. Can I pause this? No. Let me look real quick. Okay, I'm on the right track. I checked my other notes. I'm just making a mistake. That's 2. So let's just write this as this before. Let's not do this yet. So this is going to be, is that x squared there? Oh, aha. That's where it is. This x and cancels. That's where. Okay, x. And then I get L over the square root of L over 2 squared plus x squared. Now, in the event that L squared is very, very large, then this is just L over 2. Okay, that's L over 2. So this is going to be, I have L divided by L over 2, and that's just going to be 2. So I get mu naught I 2 over 4 pi x. And that's the magnetic field due to a long straight wire. So this is L much, much greater than x. And this is the other one. Okay, so that is 15 minutes. We got time. Okay, let's do this numerically. And by numerically, what I mean by numerically is to break, not integrate, instead break the problem into a finite number of pieces and get an approximation. So here's my rod, my wire, and I'm still in the middle. And then here's x, and this is the length L. And let's say I break it into 1. So 1, 2, 3, 4, 5, 6 pieces. So n equals 6. So what I want to do is to say this is delta L. In this case, delta L would not be dy. It would be L over n. Right? That's because the total length of this piece is, all these pieces have to add up to the total length. So if there's n pieces, each piece would have to be, that's the magnitude. This would be times 0, 1, 0. It is a vector. So I have delta L as an actual thing. Now I need to find the location of each piece. Now there's a couple ways to do this. Let's do this the simple way, and then we can make it a little bit better later on. So where's the bottom of this? This is at negative L over 2. So where's this piece right down here? That's my starting piece. So let's say L1, the first piece, is at 0, negative L over 2, 0. Now how do I find the next piece? That's the location of it. That's RL1 if I use my notation from before. So that's that location. Where's the next piece right here? RL2 is RL1, the old position, plus delta L. Right? Because if I take this and I add that delta L right there, I'll be right there. So I can find the location of each piece. Now, if I use my observation location RO of x 0, 0, then I can calculate d delta B. Delta B, the magnetic field due to just one of the pieces, is going to be equal to mu naught over 4 pi I delta L, which is a vector, right? I know what that is, cross R, which is a vector. I know what that is. This will be for 1. All over the magnitude of R1 cubed. And then I can just add up all the pieces. And so that's what I'm going to do. Now, in order to do this numerically, in order to add up all the pieces, I have to have some values. So let's pick L equals, I'm trying to pick let's say how long is my wire? 20 centimeters, 0.2 meters. X is, I want it pretty close, let's say 0.01 meter. The current is 1 amp. Okay, and then we can check with our other solution on the other way. So I'm going to build this in GlowScript v Python, and we're going to do this. It's going to be super awesome. Okay, so let's switch over here to the other computer. There we go. Okay, let's make that slightly bigger. No, let's make this slightly bigger. And let's say long wire B field. Okay, so let's put in our parameters here. I said L equals 0.2, X equals 0.01, I equals 1. Now, the constant mu naught over 4 pi, mu naught FP, I'm going to call it. That's mu naught over 4 pi. And that's equal to 1 times 10 to the negative 7th. I need that constant. Okay, so let's first build our wire. I'm going to put the wire along the y-axis. So n equals 6, just like I said before. I'm going to find the first position. And I'm going to make it as a ball. Okay. So I'm going to say, let's say R1. Let's say RL. Is equal to the vector. I need a place to start. Oh no, I need up here. DL is going to be equal to L divided by N. RL is going to be equal to the vector 0, negative L over 2, 0. That's my first position. Okay. Now I can say this. Let's do it the way that makes more sense. N equals 0 while n is less than n. Print n. And then n equals n plus 1. Let's save that and run it. So that what this, I'm just testing, right? When I make a loop like this, I always like to test it because sometimes I do dumb stuff. And so this goes from 0 to 5, and that is 6 numbers. So it did do this loop 6 times, so that's good. So now instead of printing in, let's just make a sphere. So I'm just going to put the sphere there. Sphere position equals, watch this, equals RL plus vector 0 n times DL 0. I should have had DL as a vector. I should. Let's do that. So let's say this. DL is a vector times vector 0, 1, 0. There. Now I can just say this. Plus n times DL. So the first time through this, it's going to be at RL, right? It's going to be right there. And then the next time I'll add on 1 length, and then I'll add on 2 lengths, and so forth. Okay, that's my sphere. I need to give it a radius. So let's say it's L over 10. I'm just picking. And let's leave it as white. Okay, let's see what that does. There. 1, 2, 3, 4, 5, 6. Done. Looks like it works. And now let's just check. What if I make n equals 60? Done. See? It's a little thick. Let's make this n over 40. That looks a little bit better. Okay. It's just a visual thing. It doesn't really matter. So let's do this. I want to see if I can't calculate stuff from there. Let's say, put up here, RO is the observation location. It's a vector x, 0, 0. RL. Let's say this. RL equals RL. Let's say R start. That's what I need to do. Let's call this all R start. R start plus n times DL. And then down here, just put this as RL. And let's just run, make sure it's working. Okay, same thing. Let's put this back at 6. Now, you'll notice that they're not touching because they're spheres, not lengths. And I can make them a cylinder later, but I'm just... Yeah, let's do that. Let's make that a cylinder. The position is there. The radius, I need an axis. Axis is from the beginning of the cylinder to the end, so that's just going to be DL. I think that should work. And the only problem with this is you can't tell that it's individual pieces, but I guess I can make that axis DL, so 0.95 times. So there's a little space in between them, just a visual space. There, that looks great. Look at that, that looks great. Okay. Okay, so now the next thing I need to do is to calculate R, right? The vector from the RL to observation location. So R equals RO minus RL. See, I already got that. Okay, now I can go ahead and calculate dB. Oh, up here I'm going to do this. B equals vector 0, 0, 0. Now down here, dB equals mu naught 4 pi, that's my constant, times I delta L cross R. So I'm going to say cross, it's a built-in function, I times dl cross R. All of that divided by the magnitude of R cubed. Now I'm going to add that to my initial function. Look at that. Look what I did. You can't even see my awesome thing that I made. See? Okay, now you can see it. Now I'm going to add that, so B equals B plus dB. And that's going to be it. Now let's go ahead and make an arrow. Arrow, let's call it B arrow. B arrow equals arrow. The position, it's going to be equal to POS equals RO. It's at the observation location. I'm going to need this. Let's print. Actually, let's not do this first. Print B. So run it. Okay, so there it is. That's important. 3 times 10 to the negative fifth, because my scale, I want to have a nice scale. So I'm going to say B scale. Let's say 1 times 10 to the negative fourth, 1 times 10 to the fourth, 1e4. Let's see if that works. So now position RO, axis is going to be equal to B scale times B. Because if I just did B, it would be 3 times 10 to the negative fifth meters long, and you wouldn't be able to see it. And I'm going to put color equals color dot yellow. I think that'll work. Okay. It's too big. So I want to make this smaller. 3. There. There you go. There's your magnetic field. Let's go ahead and calculate. There's my magnetic field. Let's print this as B numerical equals B Tesla. And then I can calculate the theoretical version, BT equals, now I'm going to get out my equation from before. I'm looking at my equation right now. It says, let's see if I can get this, mu naught over 4 pi, so it's going to be mu 4p times I times x times L over 2 divided by x squared. Oh, I don't need to do that. It's x. Get rid of this one. That's just silly. Divided by x times the square root of, let's go ahead and say L squared divided by 4. Oh, I need this. That's going to be, I think I need to do this. L squared divided by 4 plus x squared. And let's print that out. Print B theory equals BT. And that's just a scalar, that's fine. Let's run it and see what happens. It didn't print it. Can't, mu, oh, see, I can't spell. It's mu 4 pi, not the F. Okay. Not close. Not close at all. Let's just, and one of the things here that we have a problem with is that all my things are shifted. I'm going to make a better calculation right now because my DLs are right down here and here. They're not in the middle of those things. So I can fix that by just adding on to each position the start. If I just say the start is equal to, I just shift this up as negative L over 2 plus dl over 2. Because now, imagine I'm like right down here at the bottom, and that's the length of L. I want to shift that up to right there. In the middle is I have to add in half the length of that. Now the next ones, I just shift up delta L. Should all work. And it did not work. Can't add a vector and a scalar. Oh, this should be mag. I forgot I made that. Check that out. I mean, that's like pretty good. Look how that's with 6 pieces. I broke it into 6 pieces. Now, it doesn't look right though, because there's my thing in the middle. It's not in the middle. It should be right here. Huh. What the heck happened? Why is that off? I guess I moved my starting location. Negative L over 2 plus dl over 2. Mag dl over 2. And then when I L start, plus n times dl. Well, it's working, right? It's definitely working really well. And that, let's just increase this to 60 pieces. Okay. What did I do wrong? That should not have changed. Let's try. The one thing I couldn't think of is that we're really close to a piece. Let's say 20. 8. 6. 6 worked. And let's just do 7. See, 7 is way different. And let's do 5. I have to have done a calculation with my steps. Yeah, 5's real different too. Okay, so let's just check this over. So delta L, dl is L over n, that's the correct length, times the vectors, that's right. R start is the vector 0, negative L over 2, that's down here. So if I get rid of it, what if I get rid of this? Let's try this. Let's run this. And it's different. Now let's change this to 60 and run it. It's different. Let's see, 20. Something weird's happening. So I'm getting such a real wide variety of answers. So 22. So I get 2 times 10 negative fifth. I shift this up and I get still something close to 2. If I go to 30. I think that's actually okay, right? So they're all close to 2 times 10 to the negative fifth. Yeah, so I must have done an error down here. 4 pi times I times L over 2, no, times L. Let's try it. There we go. Okay, just a dumb thing like that, right? But it looks like it's working. I'm pretty happy. I want to show you why this numerical calculation is better. Okay, what if I want to find, what if this is a long wire but not infinitely long, and I want to find the magnetic field up here near the tip, right? The other equation won't work. It's not going to give me the right answer because actually I think it might work, but I'm going to do it anyway. So let's just change this our observation location to x, and let's say L over 2. And see, it did it, right? There's my magnetic field right there. Let's move x further away. Let's say 1. Now, you're not going to see anything because my B scale is too small. So let's just make this 10 times as big. And there you go. There's the magnetic field. And in fact, we could have any shape of wire, right? It doesn't have to be a long straight wire. Any shape of wire is going to work. I can bend it around in whatever I want and calculate the magnetic field due to each individual piece and add them all up. And then in the case of a long straight wire, it's actually pretty easy. They're all in the same direction. But in the case, okay, so what isn't easy is that's what I'm thinking about right now. Let me switch over to the paper and show you what would happen if you want to do it at the top there. Let's say I want to find the magnetic field up at the top. So I would have my wire. and then I want to find this location right there. So now our O is going to be, let's say this is x L over 2, so this is going to be x L over 2, 0, and then I still have the same thing for the piece. RL is going to be equal to 0, what did I say before? dy. No, it's 0, y, 0. So the vector r is going to be equal to x L over 2 minus y, 0. So it makes it a little bit more complicated in the integration, but I think it's actually possible to do that integration. I haven't done it, but still I like the numerical way too. I like it both ways. So okay, so I'm going to link the code down below, and so you can play with it and have fun with it. Hopefully this gives you good insight into how to calculate magnetic fields, but if not, at least maybe you had fun doing this, because I sure did. I will talk to you later.